Okay, this is section 4.5, and we're going to talk about these things called determinants, and we're going to use them for this special rule called Cramer's rule. Like I said earlier in this chapter, one of the really nice applications of matrices and why we teach matrices immediately following systems is because we can use matrices to solve some systems of equations, and this is going to be our first way to do that using these things called determinants. So let's talk a little bit about what those are. So determinants, it's a measurement that only square matrices have. And there's a lot of different applications that knowing what the determinant of a square matrix is can help you with. The first one that we're going to look at, and the big one that we're going to look at least here in this class, is solving systems of equations, all right? So it's really just a way to measure different matrices, and there's certain procedures that we can do with that that'll help us determine what the determinant of a matrix is. So let's talk about that both for 2x2s and 3x3. So when you have a 2x2 matrix and you want to find its determinant, another name for that, as it says here on the slide, we call that a second order determinant. Okay, you don't necessarily need to know that vocabulary. The idea for a 2x2 determinant is you just take the two diagonals, multiply them, and subtract them. So like we have here in this example, in this formula, we do A times D, and then we subtract it B times C. All right, so here's an example down at the bottom of this slide. We have the 2x2 matrix 5, negative 4, 8, 9. By the way, do you notice these bars that look like absolute value bars? When we see a matrix written with those bars, that's basically asking us to find the determinant of it, all right? It's just a symbolism thing. The other way we can notate determinant is if we put those three letters, DET, det, in front of a matrix. That's like saying find the determinant of this matrix. Anyway, back to the problem at hand. If we want to find the determinant of this given matrix, we cross multiply. So we do 5 times 9, which is 45, and 8 times negative 4 is negative 32, and we subtract those two products. We do this one first, and then this one second, always. That's a big deal, because we're subtracting, so the order matters. So if we do the subtraction, we'll change that to be plus positive 32. So the determinant of this matrix is 77, and that number, like I said, will come in handy when we talk about Cramer's rule. All right, so here's a few more we can try. All right, so the first one we'll cross multiply. 6 times 0 is 0. And then we do the right diagonal. Negative 1 times 4 is negative 4. 0 minus negative 4 becomes positive 4, so that's the determinant of that matrix. All right, we'll do the one on the right here. So we cross multiply the left diagonal. Negative 6 times 10 is negative 60. We multiply across the right diagonal. Negative 6 times negative 8 is negative 48. Subtract those two. Negative 12 is my determinant. All right, at this point, pause the video and try a couple of the second order determinants that are on your note sheet. Let's look at 3x3s, or third order determinants. These are a little bit weird. Pause the video, write down these steps of how to do it. I think it's much easier if you write down the steps and then I'll talk my way through it with the next slide. Okay, so when you're ready, start the video back up again and I'll do an example with the diagonal rule. I hope you got those examples down, or the procedures down, excuse me. We're going to do a couple examples to kind of go along with that procedure. So we have a matrix here going from left to right. We have 3, negative 2, negative 1, 2, negative 1, 0, 1, 2, negative 3. Now, like our diagonal rule says, the first thing I want to do is I want to take the first two columns and rewrite them to the right of the given matrix. So column 1, 3, 2, 1. Column 2, negative 2, negative 1, and 2. Now what I'm going to do is, starting at the top left corner of the matrix, I'm going to draw 3 diagonal lines. And I'm going to multiply all the numbers together in each of those diagonals. So in the first diagonal, I have 3 times negative 1 times negative 3, that's 9. Negative 2 times 0 times 1 is 0. Negative 1 times 2 times 2 is negative 4. I add those up and I get positive 5. Now, starting from the right corner of the original matrix, I draw 1, 2, 3 diagonals again. I did this in blue to keep things color-coded. And again, all three of the numbers that are hit in each of those lines, I multiply them. So in the first line, we've got 1 times negative 1 times negative 1. That's positive 1. 2 times 0 times 3 is 0. Negative 3 times 2 times negative 2. That's going to be 12. I add those up. I get 13. Now, I take the 5 that I got from the red diagonals, the 13 that I get from the blue diagonals, and subtract them. And I get negative 8, and that is the determinant of that 3 by 3 matrix. Okay? Tedious, but not terrible. Let's look at another example. Okay, 8, 0, 3, negative 4, negative 5, 4. That's what's in my first two columns. So let me recopy that to the right of the matrix. Okay, now we'll start again, top left, 1, 2, 3 diagonals. We multiply. So negative 8 times negative 5 times 1 is 40. Negative 4 times negative 8 times 3. That's going to be, let me get my calculator so I don't make a mistake. That's going to be 96. And then 4 times 0 times 4 is 0. When you have a 0 in a diagonal, it's easy because it basically cancels everything out and makes it a 0. So when we add that up, we get 136. So that is our red diagonals. Now we'll do it again, starting at the top right element of the original matrix. Go 1, 2, 3 diagonals, and we multiply. 3 times negative 5 times 4 is going to be negative 60. There it is. Negative 8 times 4 is 256. And then negative 4 times 0 times 1 is 0. When you add those up, you get 196. So now we subtract 196 from 136, and we get our determinant, which is negative 60. Okay, you have a couple more examples of 3 by 3s or third order determinants that I'd like you to try. Please pause the video and do that. And then when you're ready, we're going to talk about putting this all together with Cramer's rule. Okay, so hopefully now you've practiced doing a little bit of determinants by hand. Don't worry, your calculator does have a way to do determinants. For right now, I want to just do it by hand in class. I will show you how to do this with your calculator. So what we do, or I should say, what we can do with determinants is we can use them to solve systems of equations. And this guy Cramer, he doesn't live across the hall from Jerry Seinfeld, he's a different Cramer. He came up with a method of using determinants to solve systems of equations of all different sizes, okay? We're only going to do 2 by 2s and 3 by 3s because that's as far as we get in Algebra 2 is calculating determinants of that size. But do realize that if we had a system with 26 equations and we used every letter of the alphabet, we actually could use Cramer's rule to solve that system. All right, so here's the steps of how we do it. Again, it's a little technical. So why don't you copy this stuff down into your notes, pause the video and do that, and then when you're ready to see this done as an example, pick up the video again. Okay, so let's do a 2 by 2 example of Cramer's rule. So we've got the system 7x plus 3y equals 37, negative 5x minus 7y equals negative 41. Now, if you did try to use elimination or one of the other methods we talked about in Chapter 3, you would probably hate me because, look, 7, 3, negative 5, negative 7, they're pains in the butts to try to do elimination with. They're all pretty much, well, they are all prime numbers, so there's really no good way to get one to eliminate, one of the two variables to eliminate, without having to multiply each of the equations by something different. Okay? So instead, why don't we try Cramer's rule? So here's what Cramer would say. Cramer would say, write this matrix C. C stands for coefficient. Okay? So we'll take the coefficients of this matrix and put them in just as we see them in order. The X column first, the Y column second. Okay? Then here's what Cramer says. He says, okay, write two more matrices for me. This thing called C subscript X and this thing called C subscript Y. Let me explain what the subscripts mean. Basically what they mean is now, take the X column out of C and replace it with what's on the right-hand side of each equation. So 7 and negative 5, the X column pops out. 37 and negative 41 pops in. The 3 and the negative 7 just stays right where it is, the Y column. Okay? We do the same thing now with this CY. The X column stays right where it is, but now we pop out the Y column and we replace it with 37 and negative 41. So now here's what Cramer would tell us to do. Take determinants of each of these matrices. So we'll take the determinant of C. We go across our diagonals. We get negative 49 minus negative 15. Our double subtraction, we make that plus positive. This becomes negative 34. Then we do our determinant of matrix CX. Again, we cross multiply. 37 times negative 7 is negative 259. Negative 41 times 3 is negative 123. Plus plus becomes negative 136. And then we do CY determinant. Negative 41 times 7 is negative 287. 37 times negative 5 is negative 185. Negative 287 minus negative 185 is going to be negative 102. So after we take these three determinants, now we can actually solve the system. X must be the determinant of matrix CX divided by the determinant of matrix C. So we take these two numbers and we divide them. So negative 136 divided by negative 34 is going to get me X equals 4. We'll do the exact same thing again with Y. So we'll take the determinant of CY and we'll divide it by the determinant of C. Now we get negative 102 divided by negative 34, so Y has to be positive 3. So the solution to my system is 4, 3. You could have gotten that from all the other methods. I'm sure some of you may say, this is a pain in the butt, why would I do it this way? It actually comes really in handy when we do a 3 by 3. You might think this is just as tedious as elimination, but not as error prone as long as you set everything up correctly. Also, if the system doesn't have an integer solution, this will get you a more precise answer without having to deal with fractions so much, because all you're doing is you're just dividing some numbers at the end. Alright, let's take a look at a 3 by 3 example. Oh my goodness, there's no coefficients of 1 here. If you tried to do elimination with this, you would not be a happy camper. So why don't we try doing this with Cramer's rule? So let's set up our three matrices. First, we take all our coefficients and make matrix C. Then we do CX. So we're going to take that X column, we're going to pop it out, and we're going to replace it with negative 49, negative 22, and 55. All the other things stay right where they are in the exact same position. You don't move columns around. You just take out that first column and replace it with the right-hand side. We'll do the same thing with CY and CZ. Okay. Now we replace that with negative 49, negative 22, and 55. And again, the Z column stays the same. The X column stays the same for CZ. The Y column stays the same, but the Z column gets replaced with negative 49, negative 22, and 55. Here's what I want to do now. I want to kind of give you a chance to explore this a little bit on your own, pieces of it. I want you to pause the video, and I want you to take a few minutes, and I want you to get the 4 determinants of the matrices that are on our slide right now. When you're ready to roll, pick up where you left off with the video, and I'll give you the answers, and we'll figure out what X, Y, and Z has to be. Okay, so by now you should have calculated the 4 matrices and their determinants. So for the determinant of matrix C, I got 381. For the determinant of CX, I got negative 1143. For CY, I got 2667. And for CZ, I got 762. So now to get X, Y, and Z, all we got to do is divide determinants. CX divided by C, so that's going to be negative 1143 divided by 381. That's going to be negative 3. CY over C, that's going to be 2667 over 381. That's going to be 7. And then CZ over C is going to be 762 over 381. That will be 2. So our ordered triple for this system is negative 3, 7, 2. Okay, I did give you some more to try with this 2x2s and 3x3s. Have it a go, and I will talk about it more in class. Have a good one.